Okay. Good morning, everybody. The latest rage, it seems like, on YouTube Math is functional equations. There's plenty of interesting topics out there, but this seems to be very prevalent right now. And the source of this is the Cyber Math website, one of the finest math presentation platforms on the web. And I just think these problems are cool. You're so used to working equations where you're trying to just find a scalar value, or irrational value or something. And here the unknown is actually a function. You're given some clues on how the function behaves at various inputs, but you don't know the function, and you're supposed to recover that function in much the same way if you were solving a cubic equation. You would get the 3 zeros of the cubic equation, where the unknowns are numbers. Here the unknown is a function, and it takes some getting used to. Now, just a few comments about how I attacked this problem. I noticed that there was a degree 2 term here. XY is actually a degree 2 term. X to the first, Y to the first is degree 2. And I thought maybe the linear assumption isn't going to work here. Maybe assuming that the solution function is linear will fall prey to the fact that we have a degree 2 term right here. But everything else was linear looking, and so went ahead and went with this assumption that the parent function, the potential solution function, is linear in form. I use the word W just because it seems like X and Y is getting overloaded here. It's just psychological baggage, I guess. But I'm using a different variable here just to keep the symbol straight. Now, so let's move along here and get into the solution. Now, here I go with my high-tech way of animating. I'm just deleting lines here, ladies and gentlemen, to get the work up here where everything's comparable. Now, you can see what I did. I wrote down the left-hand side here, f of xy plus 1. And you can just see, rather than go through all this, I think you guys can see what I did. I just made the substitutions in the appropriate places. This piece right here is still the left-hand side of the equation, right? And this piece right here, of course, is just the right-hand side of the equation. Now, the rest of this is more or less just about collecting like terms and equating coefficients, it turns out. Now, my concern that I had was, I mentioned earlier the XY term, it seemed like it could be a thorn in our side because it is a degree 2 term. But notice when you go through all of this, the AXY terms do cancel right here, which is nice. Okay, that minimizes the length of the computations, if you want to call it that, or the collecting of like terms and all that. And so this is the result of subtracting AXY from both sides, and then you're left with this. Now this looks peculiar, but one of the commentators at the Cyber Math website politely said he didn't think making the assumption of linearity was a good idea, that there's a more direct computational way of doing it. And I understood what he was saying, but I happen to disagree. I think that you're better off doing it this way because you can actually check your function a little bit easier in the parent equation. That's not actually true completely. They just omitted that part of it really at the Cyber Math website. But in any event, it may look superfluous here for me to put the 0x here, but hopefully you can see why that's important. It makes it very, very clear that you're going to have to equate this 0 with b minus a. 0 is the coefficient of x on the left-hand side, and b minus a is the coefficient of x on the right-hand side. All right, and that I remember people used to be bothered by that when I was teaching this. I wouldn't explicitly write down 0x, and they wouldn't know why I was setting the coefficient of x on the other side equal to 0. So some people are very explicit. They need to see it, and my hat's off to them for being that way. There's no need to leave that out and make it be part of your imagination. So that leads to some fairly simple algebra. Now, just one more last comment. I know I'm going on and on here, but a plus b over here would be the constant term on this side, right? It has no dependency on x. And so 6 minus b plays that role on the right-hand side. So that's why we equate a plus b and 6 minus b right here. Now this leads to some straightforward arithmetic where you get a is equal to 2 and b is equal to 2, and I won't describe that. So if you go with the truth that a equals 2 and b is equal to 2, you go back up here to the form of our solution and just substitute a equals 2 and b equals 2 into the appropriate places. And this is our proposed linear solution. Now, notice that I'm careful with my language here. I said it appears to be, right? It appears to be. And again, I'll repeat, this is where the CyberMath solution sort of stopped. They verified it, I think, with maybe one number or something. But see, I think this part right here is just a very crucial phase of the problem. This is our alleged solution. Just think back to when you're doing scalar, when the answers are scalars or real values. It's often the case you'll substitute your proposed solution back into the original. Now that gets skipped a lot, but in many cases, if you're working a complex equation, you do want to check to see if your answer is right rather than just stop. So that's what I did right here, and this is the part that I like. This is the original left-hand side, right? This is the original left-hand side, correct? All right, and then this is the original right-hand side. So if you work it out, and I color-coded this for me and you guys, you get that cross term comes back into play when you actually check your solution. And I color-coded it so it makes it very evident that the verification works out. You get the same thing when you evaluate the solution at the left-hand side and the right-hand side. Y'all, I hope you enjoyed that, and I'm going to go ahead and shut this down to keep the video below 10 minutes. Talk to you later.